All right, hi students, welcome back to the Science 10 classroom. I don't know why I do jazz hands every single time, but I do because you're not getting special effects. It's just not happening, okay? So we're going to talk about what affects energy today. So you were given a thought activity to do first that looked somewhat like this, but it was actually in the activity and you're supposed to record your answers down. So the main thing you should have gotten out of that is based on your answers for the experiment 1, having to do with mechanical kinetic energy, what do you think affects it? So it had to do with the size or the mass of the mass of the sorry, I just realized I was sharing the wrong thing. The mass of the object and the speed at which it is coming at you, or the speed at which it's moving. So hopefully what you wrote down for that was that for kinetic energy, and even though I've kind of switched these two around, so for kinetic energy, the things that affect it are the mass, so how much matter it's actually made up of, and the speed at which it's moving. And in physics, we actually call this velocity because eventually you're going to be talking about the direction of the speed. So velocity is known as a vector because it has magnitude and direction. And yes, there's a Minions reference in there if you caught it. All right, so the second thought activity, experiment 2, had to do with gravitational potential energy. And what you should have got out of that is that what affected it, what made a difference to whether or not it was something that you were concerned about or not, was the mass and the height. So the equation, so potential energy, which I am more partial to writing it as EP, but you'll see it written each way, is calculated by taking the mass of an object, multiplying it by the gravitational constant. The acceleration due to gravity on Earth's surface is 9.81 meters per second squared. On different planets, it's different because it has a different force of gravity. But the force of gravity on average on Earth is 9.81 meters per second squared. And then height. Okay. Kinetic energy, EK, is calculated by half times the mass and the velocity squared. Now there's different types of units you can use in there. We're not going to talk about that at the moment. We're just going to talk about the concepts. So the two things that affect gravitational potential energy is the mass and the height at which it's held above the surface. And what affects kinetic energy is the mass and velocity. So if you want to take this lovely little beautifully constructed diagram, if you have a bowling ball that's not moving, that's just resting at the very top of this beautifully drawn hill, it has a lot of potential energy. It's maximum potential energy. It's not going to be lifted up from there, at least not according to our diagram. And it's not moving. So it has very little or zero kinetic energy. If you were to give it a little nudge and that bowling ball were to fall down, or maybe there was something in the way to prevent it from falling down and you pulled that out of the way, all of that potential energy ends up, as it's falling down, it ends up being lost because the height at which it is above the surface heads towards zero. And eventually when it goes to the bottom here, it has no height, so it has no potential energy. Where did all that energy go? Well, you have to think about the other thing that's involved here, and that's the kinetic energy. At the beginning, there's no kinetic energy, but as it starts to go down, it starts to speed up. So all of a sudden, it's gaining energy. But energy cannot be created or destroyed, so that energy has to come from somewhere. And where is it coming from? The potential energy. So as the ball is falling down, the potential energy is being transformed into kinetic energy. So at the end, it has very little or zero potential energy, and it has the most amount it will ever have of kinetic energy. Okay. So just to kind of go back over a little bit more thoroughly, the law of conservation of energy. Energy is neither created or destroyed. That is supposed to be an O. It's supposed to be an S. It is either transformed, like I just explained, transformed. It's going to go off road there, from one form of energy to another, or it is transferred. So unfortunately, we don't have time with this new format of learning opportunities to go into the transfer of energy. The idea of transfer of energy is the idea of, say, boiling a pot of water on an element. So the heat from the element gets transferred to the heat in the pot, which gets transferred to the heat in the water, which gets transferred to the air and then maybe transformed. So that's still all thermal energy, but it's being transferred to one object to another. And another example is why you don't pick up like a spoon that's been resting on an element on the stove that's been turned on, because the heat transfers from the hot element down the spoon. If you were to touch it, it would transfer from the spoon to your hand, and that wouldn't feel good. All right, so the total energy before something will always equal the total energy after, again, because it's neither created or destroyed. Some of it can be lost, but it's not actually lost, it's just transformed to a different type of energy that's not impacting the system you're looking at. Again, energy transfer is energy stays in the same form, but just moves to different objects. And energy transformation is the form of energy changes. Some additional notes: non-useful energy is often described as lost, but it's never lost. It's usually just turns into heat, or lost in friction of heat and transformed into heat. An open system exchanges matter and energy with its surroundings. So if you were to keep the pot lid off, all that heat that's going on inside gets transferred to the environment around it, so it doesn't stay inside, which is why it takes longer to boil a pot of water if it doesn't have a lid on. A closed system only exchanges energy with its surroundings. An example of that is a pressure cooker, where nothing's really getting out. It's not perfect. There always is a little bit escaping, but I'm going to talk about that when we talk about the isolated system. So the isolated system doesn't exchange matter or energy with its surrounding. An example of this is an insulated pot, but in reality, we can reduce but not eliminate energy exchanges entirely, because no system is perfect. We just cannot create something that perfect in the lab. There's always going to be a little bit of transference and a little bit of transformation. All right, so that concludes our lesson for today. I hope that helped and made sense, and I hope you had a great day. And if you're really enjoying this stuff, I've included an extension activity where you actually calculate potential energy and you calculate kinetic energy with math. But you don't have to do the extension. It's for those who are interested and for those who are considering going into Physics 11. Again, I hope that you enjoyed the video. I hope it helped. I hope everyone's having a great day, and take care.